Okay, so this will be a quick solution to the truss that we talked about today in class. As you see, you get 200 pounds of being applied at point C, and point C we said is 6 feet from point A and 3 feet from point B. And we said this has an angle of about 56 degrees. And so we're trying to figure out how much internal force we have on this truss right here that we're going to call AC. Okay, so the first thing that we're going to do is we got to figure out the reaction forces. We're going to have a vertical reaction force at B, R, B in the Y dimension. We're also going to have a reaction force at A, R, A, Y, and those are the two reactions that are holding up the truss. So in order to do that, we know we have to first choose our point of rotation. Remember I said to choose the pin, and around the pin we have two moments. We have the moment at 6 feet, which is 200 pounds going down, and we have the moment at 9 feet away from A, which is reaction B times 9 feet. So basically what we can do is we can set those two moments equal to each other, and so I can say 200 pounds at 6 feet has to be equal to reaction force B in the Y dimension at 9 feet. And when I go and calculate that, I will see that reaction force B in the Y dimension is equal to 133.3 pounds. So RBY is 133.3 pounds, which means that our AY must be whatever is left over to make up the total of 200. Because if we have 200 pounds pointing down, we have to have 200 pounds pointing up. So this would be 66.7 pounds pushing up at A. Okay, so now let's zoom in. This gives us our external forces. Remember we said there's no RAX because there are no external X forces, right? The only external forces is 200 pounds down. So we have a reaction vertical on both the pin and the roller. So now we'll zoom in at point A, okay? And looking at point A, this is what we have. I'm going to redraw it as a free body diagram, and this is called force AC, and this is our angle of 56 degrees. Now, because we know RAY is acting right here, and it has a force of 66.7 pounds. And we know that the bridge is at static equilibrium, meaning the forces are balanced and it's not moving. Since that is the case, we got to have some force right here that's pushing down with the same amount of force as this one is pushing up. Otherwise, the bridge would accelerate up. So there has to be some force or some component of a force that's pointing down right here that also has a magnitude of 66.7 pounds. As we mentioned in class, that thing that's pointing down is the vertical component of this force AC. So that is force AC in the Y dimension. And force AC in the Y dimension has to equal 66.7 pounds. Once we know that, we can use our trig functions to figure out what the force of AC is. Because if this is 56 degrees, we can do complementary interior angles, and we know that this angle is 90 minus 56, so that's going to be 34 degrees here. And now we know this angle, we know our adjacent, and we're going to solve for our hypotenuse. So we can come look at our equation. Adjacent equals hypotenuse, A, beginning of the alphabet, cosine, beginning of the alphabet, theta. And we can plug in the things that we know. And now we know adjacent is 66.7 pounds. And we know we don't know the hypotenuse, but in the end it's going to be the internal force of AC. and we know theta, and theta is 34 degrees. So if we divide this side by cosine of 34 degrees, and we divide this side by cosine of 34 degrees, we now can find that this AC force, the internal force here, is going to be 66.7 divided by cosine of 34. I can't solve that because I'm filming this with my phone and my other calculator is at school, but that should give you a boost anyway. We'll talk more tomorrow.